The third question here says, two parallel infinite line charges with linear charge densities plus lambda coulomb per meter and minus lambda coulomb per meter are placed at a distance of 2r in free space. What is the electric field midway between the two line charges? Now, we look at a figure here which explains the question. We have two line charges here, uniform linear charge distributions here, and we need to find the electric field midway between them. And one of the line charges is positive and the other one is negative, and they have the same linear charge density. The separation between these two line charges is given as 2r. Now, you know that if you have a linear charge distribution, a uniform linear charge distribution of charge density, linear charge density lambda, the electric field at a separation r from it would be equal to E, the value is given by lambda by 2 pi epsilon naught r. Now, if lambda is positive or if the line charge is positive, the electric field will have a direction that is away from the line charge distribution. And if the line charge has a negative charge distribution, in that case, the direction of electric field will be towards that line charge. So these are the things to remember before solving this question. Now, another thing to note here is that the net electric field at this point here, since there are two line charges in that region, E vector, the net electric field vector, will be equal to the vector sum of individual electric field experienced at that point due to each line charge distribution. So you have E plus lambda vector plus E minus lambda vector, and that will give you the net electric field at this point, and that is from superposition principle. Now, please understand that the electric field at this point here, due to the positive line charge, will be directed away from the line charge distribution. That will be towards right, and that will be the direction of E plus lambda vector. And also, there is another line charge distribution here, and that line charge distribution will exert an electric field at this point that is towards it because it's a negative charge distribution. So that will be in the same direction. The electric field due to the negative linear charge distribution will also be towards right. So you'll have E minus lambda vector, again that same direction. So you can say that the vector sum here that we need to find out will be equal to, or this value, the magnitude of electric field felt at that point, at that midpoint, will be equal to the sum of the values of electric field felt at that point due to each line charge distribution. That is because both these electric fields are in the same direction. So you can just add them up to find the net electric field. Now, from the figure, we can say that E plus lambda will have a magnitude that is equal to lambda, that is the line charge density, divided by 2 pi epsilon naught capital R, because the separation of this point where we need to find the electric field at from the line charge is simply R. And E minus lambda will also have a value that is equal to lambda divided by 2 pi epsilon naught capital R. So please understand that we don't have to put a minus sign here again. The minus sign or the negative nature of the second line charge has already been considered when we discussed the direction in which the electric fields will be experienced at that point. The two individual electric fields will both be towards right. And we considered the negative sign already there. We don't have to put a negative sign here again. Now, if that is true, E will be equal to lambda divided by 2 pi epsilon naught capital R plus lambda divided by 2 pi epsilon naught capital R. Now that will be equal to lambda divided by pi epsilon naught R. That is 2 times lambda by 2 pi epsilon naught R. That's how we get this answer. And the option will be, or the electric field here will be having a unit Newton per Coulomb. That is a standard or SI unit for electric field. So when we compare the result with the options, we can say that the correct option here is option C, which says electric field at the midpoint here, midway between these two line charges, will be equal to lambda by pi epsilon naught r, that much Newton per Coulomb. That's how we solve it.